In the previous lesson, we learned how to shift discrete time signals. Now we introduce two more operations, time reversal and time scaling. Time reversal of x of n gives us x of negative n. To draw x of negative n, we flip the signal around the origin, n equals 0. Each sample at position n moves to position negative n. The value at n equals 0 stays in place, acting as the pivot point. This operation is also called folding or reflection. Let us see reversal in action. Consider x of n with values 1, negative 0.5, 2, 0.5, negative 1, and 1, defined from n equals negative 2 to n equals 3. To find x of negative n, we reverse the index. The value at n equals negative 2 goes to n equals 2. The value at n equals negative 1 goes to n equals 1, and so on. The value at n equals 0 stays at 0. After reversal, the signal reads 1, negative 1, 0.5, 2, negative 0.5, 1, now defined from n equals negative 3 to n equals 2. Time scaling for discrete time signals works differently from continuous time. For y of n equals x of mn, we multiply each index by m, then keep only the values that fall on integer positions. The systematic method is, for each value of n in the output, compute m times n. If the result is an integer index of the original signal, that value survives. Otherwise, it is discarded. This process is called decimation or downsampling when m is greater than 1. Let us find x of 2n using the divide and check method. Given x of n with values negative 1, 0.5, 1, negative 1, 0.5, 2, 3, negative 1, 2, defined from n equals negative 3 to n equals 5. For each index in x of n, we check, can n be divided by 2 to give an integer? N equals negative 3. Negative 3 over 2 is not an integer, so cross it out. N equals negative 2. Negative 2 over 2 equals negative 1, which is an integer, so keep it. We continue this process. The surviving values form x of 2n. 0.5, negative 1, 2, negative 1, 2, defined from n equals negative 1 to n equals 3. What about x of n over 2? This is called upsampling. When n is even, n over 2 is an integer, so use the value from x of n over 2. When n is odd, n over 2 is not an integer, so we insert 0. The result stretches the signal by a factor of 2, with zeros between the original samples. This creates a longer sequence with the original values preserved at even indices. Here is another decimation example to reinforce the method. Given a different signal x of n, we want to find x of 2n. We apply the same divide and check procedure. Go through each index, divide by 2, and keep only those that produce integer results. The key insight is that decimation always reduces the number of samples. If the original signal has n samples, x of 2n will have roughly n over 2 samples. Information between the kept samples is permanently lost. Let us summarize what we covered. Time reversal x of negative n flips the signal around n equals 0. Time scaling x of mn uses the divide and check method. Divide each index by m, keep only integer results. Decimation x of 2n discards every other sample. Upsampling x of n over 2 inserts zeros between samples. In the next lesson, we will combine these operations and explore periodic discrete time signals.